hide that. And we're going to just try to understand what's going on here then. And I might explain a couple more things. We're trying to understand what is going on. It says bending light, but we don't want to use that word. The exam boards don't like it because light is not a physical object. It's more that it changed direction. So when we shined light and it stayed within the same medium, the medium is the material or the space in which the wave is traveling through, and the light wave is traveling through air, and it's just still traveling through air. And so this line here, if there was this would be called an interface. And so if it was going into water, for example, then the interface is when it changes mediums from air into water. When it changes mediums, there will also be some reflection. And this dotted line, this is the normal. We always draw the normal at 90 degrees to the interface, but also it's important to realize that it's where the light ray is incident on the interface. So some people might end up just drawing the normal like this and just going, I don't know, it doesn't really matter, does it? But it does matter. It must be at that point there, and then also at right angles. So the angle of incidence, or the incident angle, is that angle there. The angle of reflection is this angle here, and the angle of refraction is this angle here. The ray of incidence is this ray here. The ray of reflection is this one here, and the ray of refraction is this one here. So let me just get my mouse back again. Right. So we've got, if I were to turn this back into air, you can see that as I went from air to water, the ray moved towards the normal. That's the normal down there. If I move it to glass, it moves even more towards the normal. And if we make the refractive index greater, it moves even more towards the normal. So now you're going to learn a bit about refractive index, but the first thing that we're going to think about is that this is more dense, okay? And this is less dense. And generally speaking, less dense means low refractive index. But not always, but generally speaking. I think in your GCSE, you generally think about it as that way, but I don't think it's always the case. Another thing to realise, and this bit's important to understand refraction properly, is that we often think of light as people will say that light is constant. Light moves at a constant speed, and that nothing can travel faster than the speed of light. Light always moves at that speed, which is 300 million meters per second. But they're not quite right there. Because, in fact, we can prove it, because if we go down to here, it's not. It's traveling slower. Okay, this isn't glass. Well, let's move it back up to glass again, so we can imagine it's glass. So when it's traveling through glass, it doesn't travel at 300 million meters per second. It travels at about 2/3 of that speed. So light does actually slow down. Okay, it doesn't move at constant speed. What the quote should have been is that light is constant in a vacuum. The speed of light is constant in a vacuum, but this isn't a vacuum. This is glass, so it does slow down. So what we want to include here, we've said that it's less dense. We want to also say that it's faster, and then it's slower. Okay. Now that's actually the reason why it moves towards the normal. The fact that it slows down. So when any wave slows down, as long as it's not incident on the normal. So if I were to do it right on the normal, then it's got nowhere else to move. So that's the only situation. But when any wave slows down, it moves towards the normal. So we're going to try to understand why that is by getting a wave diagram, and we can see they're moving more quickly here, and they seem to be moving more slowly here. Because they're moving more slowly, they're getting all bunched up. The frequency is still the same. The frequency at which the oscillation is happening, that's still the same. Because the wave's moving slower, the frequency is still the same, and that means that they're bunching up more because they're not. If it was very quickly, but then moving very quickly as well, then with each one, it would make the waves would be stretched out. Because they're moving more slowly, then you can imagine a piece of paper being pulled across while something's doing this. If it's being pulled across slowly, then the lines would be close together. If it's moving more quickly, the lines would be further apart. That's kind of like what's going on. So it slows down. It actually does slow down, and we're going to try to understand why. So if we got a wavefront, if we imagine one of these wavefronts. So in fact, I'm just going to pause it just for a moment, and if we just look at this one here, see that wavefront there. It's part of the wavefront, and what I mean by the wavefront is I mean those lines like this. Part of them has, let's just try to keep them the same width apart. So, and if I draw the interface and draw a couple more, now you can see part of the wavefront would have made its way into the next medium, and the other part hasn't. So if our left-hand side, the wavefront has, for the one we're looking at, has gone into the new medium, and it's slowed down. And so the gap between those two is slower, whereas that one isn't. So they would start to bunch up, and as a result, the left-hand would slow down before the right one would. So you can imagine if there was a wavefront that was kind of moving one direction, and this one on the left moved more slowly than the one on the right, well, the whole thing's going to rotate, right? But that's basically how wheels on a car would work. One of the wheels is going to move faster than the other one as it goes around the bend. It's going to do that. So, let me just explain that a little bit again. So whenever you move by practicing a few of these, you'll see that whenever you are going whenever a wave is slowing down, it refracts towards the normal. And with light waves slow down when they go to a more dense medium, or we can say when it goes to a higher refractive index. But the thing is, all waves do this if they slow down. But the thing is, if it was sound, for example, sound would also refract, but sound would refract actually the other way around. Sound would refract if it went into it would slow down if it went to a less dense medium. Imagine we're trying to refract a sound wave. So we've got an interface here, and now we're going from say water to air, and let's say pretend this is a sound wave. This one would move towards the. Whoops, that's not very good, really, is it? I'll do it a bit more exaggerated. This one would move. Oh dear. I can't draw a straight line there. Look. That's a bit better. Oops. This one would move towards the normal, like that. So, and this time it's the other way around, and that's because sound travels more slowly in less dense mediums. So, without at the risk of getting too advanced too quickly, you can always replay this video, right, and try to understand what I'm saying later on. But we use this idea of refraction in light to design lenses. So if we had, in fact, I'm going to so basically what a lens does is it focuses light to a point like this. In fact, I can demonstrate this with some of the tools we've got here. So let's do that actually. I'm going to get some of the tools here. So I will clear the screen of the drawings and we go to the tools and we're going to get, I wonder if I can get a couple. Oh yes, I can. Fantastic. This is what we want. This is like the top of the prism. Maybe let's do that. So, and I don't know if this is going to work, but we'll just try it out. Okay, we could do with them being a bit further apart really. So let's just do one of them. We'll have one ray going down in the middle, it goes straight through, and then one at the outside. Notice how it bends towards normal, and then it looks like is it going towards normal again? Oh yes, because this time it's going from a more dense to a less dense medium. And so if we were able to get, it'd be good if we could have a couple of lasers here, so we could have one going there, one going straight on, and then if I had another one, I could rotate this, and you can make a lens, or sort of, it's not really a lens, but, and you'd have one at the bottom, that would go towards the middle as well. So you'd have them all sort of converging to a point. They'd all would kind of converge to this point around about here. So they went through this and kind of converged like that. Now that's quite useful. Our eyes have lenses in them, and we focus the light that comes into them, and we focus it into the retina at the back of our eye. And so as we have a clear image on the back of our eye, which our brain can then turn into an image of the world. But here's the thing. There are some animals that use different waves to make sense of the world around them. So dolphins use light, but dolphins also use sound. And so a dolphin, I'll briefly get a picture of a dolphin now. So here you can see the dolphin's melon. Believe it or not, that's actually what it's called. But you see, it's roughly the same shape as a lens. It's sort of convex. It's like a curved thing, and it does the same thing as what our lenses in our eyes do. The difference being is that the dolphin's trying to focus sound. We're trying to focus light. So what the dolphin does is it takes the sound waves that are traveling through the water and it focuses it into focuses it using its melon. And so the melon is actually not going to be more dense than water, it's going to be less dense than water. So the melon is mostly made out of fat, I believe, whereas the lens in our eye is going to be more dense than air, of course. And so our lens in our eye focuses light by bringing everything towards the normal, then away from the normal, and then it focuses it together using refraction. We're refracting light. This dolphin's refracting sound waves, and so that it uses the same thing. Okay. So I'll just sum that. I'll just stop that video there.